Okay, yeah, thanks, Danilo. So our next talk is going to be from Quentin Anthony, who's a PhD student in the Department of Computer Science and Engineering from the Ohio State University. And he just finished his second year, and he's going to be presenting a paper that about a class of models that I don't think gets enough attention, which is about computer vision models that deal with high resolution or super resolution images. Right, take it away, Quentin. You have about 20 minutes. I can't hear you. I think you're still on mute.
Can you hear me okay now?
Yes, and I see your
Okay,
screen.
great.
Oh,
Yeah,
go
one
ahead.
sec. Okay. Uh, hey, thank you for the introduction, Vinod. My name is Quentin Anthony, as he said. I work in the network-based computing lab with Dr. Panda. So my focus is on Vapid 2, which is an MPI library for GPU and deep learning applications. I'm going to talk about scaling image super resolution, deep neural network training with PyTorch and Vapid 2 GDR. So first I'll introduce the state of Hpc and Dl frameworks. Then I'll present some background on super resolution, what Cuda MPI is, and distributed Dl frameworks. And then I'll summarize the concrete challenges resolved in this work. And then I'll detail the design choices that we chose to overcome these challenges. Then I'll present the performance improvements of these designs and then conclude with some future work and key takeaways of our work. So first, let me briefly introduce deep learning and its context in HPC training. Deep learning is a subset of classical machine learning where the training features are automatically extracted. Um, and the reason deep learning is so popular now, given that a lot of the theories completed back in the 80s, is that computing power has finally caught up, as a lot of us probably know, and that we're now able to train practical deep learning models in a reasonable time frame. So now I'll introduce some more about deep learning frameworks. So they allow us to easily implement and experiment with deep neural networks. And then several major deep learning frameworks have emerged. So PyTorch, TensorFlow, and MXNet would be the major DL frameworks. And our focus here is on PyTorch due to its ease of use and its popularity. Most frameworks right now are optimized for NVIDIA GPUs, but AMD GPU support is on its way. And then distributed training support within these frameworks is gaining some steam, as well as some specialized distributed deep learning frameworks such as DeepSpeed and Horovod, which we'll discuss soon. So now I'll present some background on super resolution, some CUDA MPI, and distributed deep learning frameworks that were used here. So first, deep neural network training consists of two phases, the forward and the backward pass. So training is a really compute-intensive task. So we have extremely large data sets, and we operate on them with these complex deep learning models. And as a result, MPI-driven training is on the rise. So there are three approaches to distribute DNN training. The first is data parallelism, which is the focus of this paper, where you fully clone the deep neural network across worker nodes, and then update the models at each global training step with an all-reduce operation. This is the most widely adopted scheme, and we use it in this paper. The second is model parallelism, where uh, um, you split the model itself across compute nodes. And then the third is hybrid parallelism, where you split the model across a set of nodes with model parallelism, and then you perform data parallelism across each set of nodes. So that leads me to the Mvapage2 project. The Mvapage2 project is an open source MPI library headed up by OSU, Dr. Panda. The focus in this work is on Mvapage2 GDR, which is a CUDA MPI flavor of Mvapage2, with a focus on NVIDIA GPUs and new support for AMD GPUs. Um, so the focus also is on Mellanox InfiniBand adapters. Um, we have support for ARM, x86, and OpenPower 8 and 9 CPUs. The focus here will be on Power 9 CPUs. And then lots of GPU features such as non-blocking collectives, CUDA managed memory, GDR copy and loopback, which are small message optimizations, as well as what we'll be focusing on, which is Cuda Ipc and the registration cache, as well as large message collective designs for DO frameworks. Um, so first, let me explain what Cuda Ipc is. It's an interface for communicating across GPUs within a node. It's meant for large messages, and many the advanced collective and point-to-point designs used in Vapid GDR rely on Cuda Ipc. The second is the registration cache, which enables a zero-copy transfer of large messages across InfiniBand without requiring memory registration only on cache hits. So on applications like deep learning, where we expect lots of cache hits, we want to quantify and see what the effect on training throughput would be. So previous Mvapich2 versions disabled the registration cache for deep learning workloads due to the conflict with TensorFlow's custom memory allocators, but PyTorch doesn't have such memory allocators, so we would like to apply the registration cache to PyTorch training and see what its effect is. So now I'll sort of explain image super resolution and EDSR. So many of the emerging scientific and medical applications today require high resolution image input. So some examples of that are computational pathology, satellite imagery, and climate analysis. And any super resolution model, deep learning or not, maps a low resolution image to a high resolution image. So deep learning super resolution trains a deep neural network to learn the mappings from a low resolution image to a high resolution image. So data sets for deep learning super resolution, such as div2k, consist of high resolution 2K images and sometimes low resolution counterparts. In the case of div2k, there are no low resolution counterparts provided, and the user is just expected to downsample them or provide or have a separate data set that is just downsampled versions of those images. As we'll see in the next few slides, super resolution models are much more compute intensive than classification models like ResNet. So we chose EDSR as our representative deep learning super resolution model due to its state-of-the-art accuracy and open source implementation. So here's what I was talking about the compute intensity of EDSR and deep learning super resolution models. We compare here a training run on a single V100 GPU for ResNet 50 and EDSR, and we see that the images per second for ResNet 50 is something like 360, and for EDSR it's something like 10. So we conclude here that super resolution DNNs require a lot more computation per image just from this simple check, and that super resolution DNNs could benefit greatly from Hpc to reduce training time. That leads me to Horovod. So Horovod is a distributed DNN training framework that employs data parallelism. It acts as a middleware between the deep learning framework, in this case PyTorch, and the communication backend, which we test for both MPI and nickel. Performance is strongly dependent here on allreduce, and before carrying out evaluations, we added full distributed training support to EDSR via Horovod, and then we'll be pushing that back to the public repo. So the high performance deep learning project in Mvapich2 tightly integrates the deep learning frameworks that are available along with the communication backend for both Horovod and then something more specialized like torch distributed and DSpeed. So you can see the full program stack here as we go from the model, the user application, EDSR, it goes to the deep learning framework, PyTorch, and then we distribute those via Horovod with communication backend. We test both nickel and MPI, and then we apply those on the system. So that's the background necessary for this work. So now I'll summarize the concrete challenges that we resolved here. So this is the distributed training that we performed on the Hpc system and found poor training results. Only about 55 to 65% scaling efficiency for both Mvapich2 GDR and nickel, and we wanted to see like what the cause of these are and how can we resolve them. So first, we looked into Cuda Ipc. Since PyTorch allocates all the available GPUs on a node, not just those assigned, Cuda Ipc needs to be disabled for most distributed PyTorch training runs. And this is mentioned in the user guide of PyTorch is an established practice. So the method recommended by PyTorch is to set the Cuda visible devices flag in your environment to the local rank. So every single GPU's visible device is only listed to itself. So there's no GPU crosstalk within a node. However, that would disable Mvapich2 GDR and other MPI libraries and CUDA-aware libraries from using Cuda Ipc or any other GPU-aware designs that require crosstalk. So our primary goal here in this work is, can we add an intermediate visible device list so that the communication backend can still see GPUs? And we implemented that as MV2 visible devices that allows Mvapich2 GDR to view GPUs while hiding them from PyTorch. As a secondary goal, we wanted to see whether the registration cache designs improve deep learning performance and by how much. So how do we improve the scaling efficiency and training throughput? By enabling advanced Cuda Ipc and registration cache designs and Untitled GDR for deep learning frameworks. So now I'll detail these design choices, in particular for Cuda Ipc. So first, uh, we ensure the Untitled GDR enhancements based on Cuda Ipc are properly used by PyTorch. So previously, PyTorch users have one of two options. The first option is the one I mentioned. The first option is where you run without setting CUDA visible devices at all, and you allow PyTorch to allocate GPUs, any GPU that it sees. But this implements a set, so every single GPU has compute kernels. So each compute kernel is what's actually launching the deep neural network training, and then PyTorch itself launches overhead kernels. And every single GPU will launch an overhead kernel on every single other GPU that it can see in PyTorch. And these are just memory allocated for profiling overheads or something in PyTorch. Um, but the crux here is that PyTorch doesn't respect the set CUDA.set device flags. So what they recommend is that you run with CUDA visible devices equal to the local rank here, which is what I mentioned previously in the user guide, but that disables all CUDA Ipc designs and Untitled. So we have this trade-off on whether or not I want to launch overhead kernels and allow PyTorch to waste memory, which will lead to out of memory issues for larger models, or if I want to disable my backend's IPC designs. Um, so what we contributed was we add support for CUDA Ipc calls when CUDA visible devices are set. Um, and but in order to do this, we noticed that CUDA allowed CUDA visible devices to be set and still call CUDA Ipc in CUDA 10.1. So the support has been added at the CUDA level. So as a result, we designed an intermediate layer of visible devices, MV2 visible devices, implemented in Vapage 2, which enables multi-GPU designs regardless of whether CUDA visible devices is set. So as you can see here, as a user would still set CUDA visible devices equal to the local rank, so that PyTorch can't have GPU crosstalk and can't launch these overhead kernels, while still setting MV2 visible devices equals to all devices, all GPUs on a node. So Vapage 2 is still able to use CUDA Ipc and other GPU crosstalk designs. So now I'll discuss the performance evaluation here. First up, the system that we ran this on is Lassen, number 17 supercomputer on the top 500. There are 792 GPU nodes there. Each node has 4 volted 100 GPUs with 16 gigabytes of memory. And then, as you can see here, these green links are NVIDIA NVLink, which is a high bandwidth interconnect that connects both CPUs to GPUs and GPUs to GPUs. For our software libraries, we use PyTorch version 1.8, and then CUDA 10.2, cuDNN 7.6.5, and we use the latest Vapage 2 GDR 2.3.5, as well as the publicly available EDSR model. So now I'll show the actual performance results that we got from these designs. So the terminology here in the slides is there's no CUDA Ipc and no registration cache. So this is just the default setting CUDA visible devices run. MPI reg would be no CUDA Ipc, so we're still running this default run, except this time we apply the registration cache. And then MPI opt has both the registration cache as well as the MV2 visible devices design that we mentioned in previous slides. This is optimized MPI. So we notice the MPI with the registration cache enabled, so MPI reg, we see about a 5.1% improvement on average and a 93% hit rate within the registration cache itself. We saw high hit rates across the board, usually above 85% for smaller scales, and that hit rate increased as the scale increased. We also saw MPI with CUDA, the MPI opt design. I saw up to a 26% improvement over the non-IPC designs. And here again, we're seeing, we can see at all scales that we're seeing improvements with over both nickel and the default MPI for the optimized design. We also measured the scaling efficiency. So we compare the scaling efficiency of EDSR between the optimized and default Horovod runs and demonstrated about a 15.6% improvement in scaling efficiency. But we also ran profiles. So we wanted to, the whole sort of motivation for this work was we've run ResNet models in the past, which are large, but not as large as something like EDSR. And we were able to achieve good scaling performance. But we know from past profiles that ResNet 50 messages are typically in the kilobyte range. But we see here that a good proportion of the EDSR messages are anywhere from 20 megabytes to something like 64 megabytes, which is the max that Horovod supports by default. So we applied our internal profiling tool, HVProf, to profile all reduce before and after enabling these registration cache and Cuda Ipc designs. And the latency is significantly improved after at all these message sizes. So here are the profiling results more in detail. So we see that the latency is significantly improved for larger message sizes, as I discussed, and Cuda Ipc in the registration cache is only enabled in Rapid GDR for large messages. So it's vital that we make sure that these work harmoniously with the deep learning framework and the distributed deep learning framework when we go to larger models like this. It's also critical that users first profile the deep learning workload before applying MPI designs. And I want to bring more attention to this slide so we can explain the full motivation of this work just from this table. So smaller classification models can be profiled. We saw that the smaller messages, we see here that the communication behavior is different. So then we notice that the large messages, so then we checked whether the large message designs and GDR are picked up. So we stress here that profiling each layer of the deep learning training stack that I mentioned earlier is necessary for diagnosing and overcoming these bottlenecks. So we can see up to a 45% improvement in total all reduce time after applying the rapid shoot GDR designs. So in conclusion, so I'll conclude with some future work and key takeaways that others can see. Image super resolution is growing in popularity. Deep learning super resolution models like EDSR require extremely long training times, and novel DNNs bring about novel communication bottlenecks. And the only way to see those novel communication bottlenecks is by profiling, typically. In order to effectively scale to hundreds or thousands of GPUs, we need to ensure that DL frameworks are using advanced MPI features properly. Ensure that there's no mismatch between the two. Some future work that we're exploring, we're seeing whether larger super resolution DNNs can be improved or designed with HPC in mind, and can they efficiently scale to HPC systems. We also want to work with application developers to see what novel applications in super resolution could benefit from these extremely large output images from super resolution deep neural networks. So thank you. That's all I have. If there are any questions, I'd be happy to field them.
Yeah, thanks, Quentin. Yeah, we have time for a couple of questions. I'll ask one. So just kind of from the previous speaker, Professor in the Hoffler's talk, where you looked at kind of different kinds of possible bottlenecks in your cluster, compute storage, communication. So in these super resolution models, what tends to be the bottleneck? I know you focused on kind of optimizing communication, but if you could kind of holistically look at this problem, where is the bottleneck really?
For distributed super resolution models?
Yes.
I would say that most systems don't have the bandwidth like the system that we ran on, and as you can see, they have these extremely large messages, these megabyte, some number of messages, and a lot of, unless you have like an optimized MPI or nickel design, then you're going to get a lot of contention across the links. So basically, these larger messages that we don't have in image classification models aren't accounted for. And this work is something that is a step in the right direction so that these large messages can be handled. So in a few words, large messages are your main bottleneck and problem, I'd say.
Okay, so you were seeing like a lot of idle compute, like the GPUs were idle for a lot of the time before you
Yes.
apply your optimizations. Yeah.
So if you look at the Horovod profile, there's the it takes a lot of time to negotiate the all reduce because they're so large. That was the start of the motivation of this work. For something like ResNet, that time is much smaller because messages are normally in like the kilobyte range that
Okay.
we've seen.
Yeah. Any other questions?
So Vinod, I have one question.
Yeah. Go ahead.
Yeah, hi, Quentin. Thanks for a very interesting talk. So, one question is that when you talk about the size of the message, it is related to the size of the gradients or the size of the model that is being aggregated, or when you say the size of the message is
Oh,
large.
yeah. So the gradients, but that's
Yeah,
loosely related to the size of the
a
model, I'd
model.
say.
Yeah,
So
yeah,
yeah,
yeah.
it's
And the
definitely
other,
interconnected.
yes. And the other question is that why TensorFlow 2 was not used because it has a distribute strategy, right? And it supports many distribution strategies. So why Horowatz was preferred instead of TensorFlow 2.0?
Hmm. The model itself is implemented in PyTorch. PyTorch has its
Oh,
own
okay,
distributed
okay,
communication framework, but we
okay.
opted for Horovod because we've seen that for data parallelism, Horovod is usually more efficient than
Right.
PyTorch
Okay.
distributed.
Okay. So Python. Okay. Sorry. Okay. And it's just because the model was in Python, so you cannot use the TensorFlow,
So
right?
another reason was the registration cache that I discussed. So
Right.
I, I know for sure in TensorFlow 1, and I believe it's still true in TensorFlow 2, but it's not compatible with the registration cache due to TensorFlow's memory allocators. So
Okay.
TensorFlow is pretty aggressive with how they allocate memory, and it's hard on the MPI side to work with that. So I
Right.
know that we've only tested registration cache designs with PyTorch.
Okay. So how active is Horowatz community? I know 2 3 years 2 years before, like during TensorFlow 1 point, like before 2.0, it was a very big thing. But now also is it active for non-TensorFlow type of frameworks? It is active or?
Oh, for sure. Horvath is very active. We hear a lot now about deep speed as well. So the space is more crowded. So I would say it's harder to hear from Horvath, but it's still really a really active code base.
And it is
Um, it,
still and regarding its use with TensorFlow distributed, it is used, or how TensorFlow 2.0 is taken over it for the distribution of TensorFlow frameworks?
Horvath is still a bit easier to use than something like TensorFlow
Okay,
distributed.
okay, okay.
You don't have to know as much about your system.
Yeah,
Uh,
okay,
it's easier to install, that kind of stuff.
okay. Thank you. Thank you.
All right, yeah, thanks, Quentin. And we're kind of eating into our break, so I'll kind of stop it there. I think, Quentin, if you're around for the rest of the workshop, and people can get in touch with you directly with any follow-up questions.
Thanks.
All right, yeah, thanks again for the interesting talk.
So
So we're into our first break right now, and the break is going to be for another 15 minutes or so. So we'll resume at 9:40.